Exercise 1F, inverse functions. Today we are learning about inverse functions. What you need to be able to do is graphically reflect a function in the line y equals x, find the rule of the inverse function by switching the x and y variables, and restrict the domain of a function to 1 in order for the inverse function to exist. So what are inverse functions? Might visually look something like this. It's something, the function itself is flipped. So there's some sort of flip that is occurring. Um, Really, in mathematical terms, our flips that we refer to is about reflections, and we have learnt about different types of reflections before. In fact, we've learnt about two different reflections. So if I were to draw a square root function, we know about reflections in the x-axis, and we also know about reflections in the y-axis. So here is an example reflection in the x-axis. Our original function is y equals to the square root of x, and you can see that it's been reflected in the x-axis, which means that the x-axis kind of acts like a mirror. Now, what's actually happening in this case is that all of the x values are staying the same, but all of the y values are the negative version of what they were originally. So how do we achieve this in terms of a function? Well, as we said, all of the x values stay the same, so my input is the same, but the output, I just want the negative version of it. So to get a reflection in the x-axis, we put a negative outside the function. We also have a reflection in the y-axis. So again, we've got our original function here. You can see that the y values this time all stay the same. However, the x values are flipped. So that's the one that is going to cause our function to be flipped here. So these x values are just the negative values or the negative versions of those values there. So we will put a negative in front of the x, which means that when we input the negative x value, so if I input -1, for example, it'll be the same as though I'm taking the square root of 1, which will achieve the same y value. So to get a reflection of the y-axis, we attach a negative directly to the x. So we're going to learn about a new type of reflection today, which is in the line y equals x. And this is what an inverse function is. So instead of our x-axis or y-axis acting like a mirror, instead we're going to have the line y equals x. That is going to now act like a mirror. So this is our square root function. And you can see that if that acts like a mirror, this becomes my new function here. Now, on the line y equals x, they're going to intersect because that's the point at which it's being reflected. It's kind of like when you reflect a function here, it'll always intersect at the point at which it's being reflected. Now, the key question though is how do we achieve this? What's actually happening to our values? So if you can recognize here that this is a square root function, this is a parabola. How do we get that? It's from actually swapping the x and the y value. So that's the relationship between these two functions here. If we were to swap y and x, we can see that there is a relationship between the square root function and between the parabolic function that will result in them being inverses functions of each other. So all we need to do to be able to achieve this is to actually swap our x and y value. In terms of how that happens, so instead of y, I'm going to write x. Instead of x, I'm going to write y. And now I'm just going to get y by itself. And you can see I've got the function y equals x squared. And so those two functions there will be inverses of each other. So a reflection in the line y equals x is a result of the x and y values interchanging. So we're not putting negatives in front of anything, we're just swapping the x and the y values. This is another example of what it looks like. So you can see that here again, we've got our mirror y equals x. And what happens is that all of our x and y values actually flip. So when we have a look at a coordinate here, it's 1, 0. The opposite of that would be 0, 1. So every single one of our x and y values flip, and that's what an inverse function is. Okay, so to do this, to find the inverse function, what we do is we interchange x and y. So the rule of inverse relations can be obtained by interchanging x and y and then making y the subject. Because we're changing x and y's, so do the domains and ranges. They just flip. The graph of the inverse function is a reflection in the original relation through the line y equals x, so that's what's acting as our mirror. The inverse is the same distance from the line y equals x as the original graph. We'll kind of talk about that visually a little bit in a bit. And the coordinates of the known points are interchanged by this reflection. So as long as you always swap your x and y values, that will result in a mirror reflection in the line of y equals x. As we mentioned, because x and y flip, so do the domain and range. So the domain of the inverse is equal to the range of the original. The range of the inverse will equal to the domain of the original. Any intersection between those two graphs will always occur on the line y equals x. As I used as an example, if you reflect on the x-axis or y-axis, the functions will always touch on the line that is a mirror for them. Now, we're going to talk about this one really key point here, in that only one-to-one functions will actually have inverse functions. So the reason for that, if we kind of think about, let's consider a line, for example. Maybe it'll, just to give it a bit more of an angle. So that's the line y equals x. Say we have this line here, that's fine. So the inverse function will just be it being reflected as though it's a mirror. Now, in order for something to be a function, it needs to pass the one-to-one, the vertical line test. So just looking at the red line, that will pass the vertical line test, which is the original. And the green line, again, that passes the vertical line test, which means that is also a function. But say we start off with a function like a parabola, right? At this stage, the parabola is still a function, so it does pass that vertical line test if I draw those lines in. Now, if I draw in the line y equals x and I flip it, so we have our inverse function. Looks a little bit dodgy in the way that I've drawn it. So it'll look like that. If I try to now do the vertical line test, you'll actually see that that new relation is not a function because it does not pass the vertical line test. It actually touches at more than one point. So that's why that even if I start off with a function, this one's obviously not a one-to-one, when I flip it, it becomes, so if it's a one-to-many, it becomes a many-to-one, or the other way around, if it was a many-to-one, it becomes a one-to-many. So in that, it's not always going to be defined as a function, whether it starts off originally or later on as the inverse, it's not a function in both times. The only time that it's going to be a function for both the original and the inverse is if it's a one-to-one. So just keep that in mind, and that's the reason why that is the case. All right. So let's go ahead and start some of our examples. So example 10 says, consider the function of that domain is restricted, where a is the largest possible value, such that the inverse function exists, determine the value of a. So that just comes off the fact that we spoke about inverse functions will only exist if the original is a one-to-one. Okay, so the best way to do this is to kind of sketch just so that we can get a visual idea of what's going on. In order to sketch this, I'm going to complete the square so I can find my turning point and we can find the x-intercepts from there as well. So we're going to start off with y equals x squared minus 2x minus 3. If I were to complete the square, half goes into the bracket and then minus 1 minus 3 will be negative 4. So my turning point will occur at 1 and negative 4. If I were to factorize this to find the x-intercept, so two numbers that multiply to give negative 3 add to give negative 2 will be negative 3 and positive 1. So my two x-intercepts will be 3 and negative 1. So now if I go ahead to sketch this function, what I can see is that there's an x-intercept at negative 1, x-intercept at 3, and 1 and negative 4. So it should look something like that. Just move it downwards. There we go. Right, 3, negative 1, 1, negative 4. All right. Now here's the problem. This is obviously a function. However, if I were to flip it in the line y equals x, so it'll look something like we'll have a turning point at negative 4 and 1, or something like that. This is no longer a function. It does not pass the vertical line test, so I have to make it a one-to-one. We want it to be the largest possible domain, and we can see that they've given us a restriction. It has to start from the left-hand side. So the left-hand side, moving to the largest possible value of a, where it will be one-to-one, will actually be at the turning point. At the turning point, that is the last point at which it won't double up anymore. After the turning point, it starts to double up. That's where my problem occurs. So that's still one-to-one. Anything after that is not one-to-one. So in this case, our a value will actually just be the x value of that domain, of that turning point. So our domain will have to be from negative infinity to 1, which means our a value is equal to 1. That's what will make this function a one-to-one function, given that it has to start from the left-hand side. Now, this question could have very easily said a to infinity, in which case you would have got from the right-hand side, but even then, your largest value would still be at 1. All right, now part B says find the rule of the inverse function. I have run out of space, so I'll create a new page. So to find the rule of the inverse function, you swap x and y. So if we start off with our original function, we can swap x and y. Now, the technique to this, because we want only one y, is to complete the square. That's the best way to be able to find the inverse function. So if we complete the square, which is what we did before anyway, we can see now we're down to 1y, and all we have to do is rearrange our function to get y by itself. So that'll be x plus 4 is equal to y minus 1 squared. Take the square root of both sides. Now the thing is, of course, when you take the square root, it's plus minus, but because our domain is negative, that means we're looking at the negative square root. And then finally, we will take that 1 over to get y is equal to this function. So that's the function there. We can also state the domain. So remember, the domain of the new function is equal to the range of the previous function. So the range of the previous function was -4 to infinity. So in this case, x will be an element from -4 to infinity. So that's domain of f inverse, which is also the range of the original function. All right, part C then says sketch the restricted graph of y and its inverse on the same function. Okay, so we've already kind of done this, at least sketching the original function before. So we're going to now do it with restricted domain though. So we found that our intercepts, we had one at -1, 0. Just looking at this graph, the y-intercept will be at -3, and we'll also have a turning point at 1 and -4. So I'm just going to go ahead and try to sketch it as well as I can. So we'll say that that's 0, 3, -3, sorry, and 1 and -4. Right, now to find the inverse, all you have to do is swap all of your x and y values. So if before I had an intercept at -1 and 0, my new intercept is going to be at 0 and -1. So that should be over here. I had an intercept at 0, -3. Now I'll have another intercept at -3 and 0. And finally, my turning point was at 1 and -4. Now it's going to be at -4 and 1. So we'll try to draw a nice parabola through it. I'm not sure how it's going to kind of go with my iPad. The scale was off. It's very hard when I'm trying to get it to click into a specific shape. Let's try again. If not, I'll just do it by hand. Scale's not quite there. I reckon that's as good as we're going to get it. So that's -4, 1. That there is -3, 0. And that is 0, -1. So scale is not the best. Also, your graph should not curve upwards. So if we were to continue this, it should kind of go downwards instead. But there you go. So that's the general idea of the inverse and its original. Now, it might look a little bit wonky. That's okay. You can see that if I draw the line y equals x, it is intersecting at that point, and it kind of looks like a mirror reflection. It should at least look like it. Now, part D says give the domain and the range for both graphs. So if we were to consider f of x, our original function, we can see that the domain, restricted domain, is from -infinity to 1. Oops, we don't include -infinity. And that the range is from -4 to infinity. And then for the inverse function, it simply flips. So the domain is from -4 to infinity, and the range is from -infinity to 1. Great. So there you go. That is your inverse function that has been restricted. Okay, so let's discuss this idea about the point of intersection between f of x and f inverse of x. As we've already mentioned, it will always intersect along the line y equals x. So to find the intersection, what we generally do is we make two functions equal to each other, but sometimes it's really yucky to do that, particularly if you're making a square root equal to a square function. It's going to be really hard to find x by itself. Because we know that the function also intersects with the line y equals x, the easiest way to do it is to actually just make either the original or the inverse function equal to x. So all three functions are intersecting at the same time. So you might as well use that to your advantage and make it equal to the line y equals x. So just make it equal to x rather than trying to make the two functions equal to each other. And that makes it so much easier to do. Okay, so let's give this one a go. It says consider the quadratic function that is defined by f and so on. Find the largest possible value such that f inverse exists. So very similar to what we were doing before. We've got a quadratic, and we know for it to exist, we're going to find out at the turning point. So complete the square. For the middle, that'll be -9 plus 4, which will be -5. My turning point is at 3, -5. So if I were to give this a really quick sketch, we know that the turning point is at 3 and -5. In terms of intercepts, two numbers that multiply to give 4 add to give -6. I don't think there are any two nice numbers that do that, which is okay. We don't need exact values. Anyway, the point is whether the graph looks like this or the intercepts are both positive, I'm not sure. For the domain to be -infinity to a certain value will surely be 3. So the largest possible value, a will equal to 3. So for part B, we need to go ahead and sketch both of the graphs on the same set of axes, so the original graph and the inverse. The original graph, which is this one here, we just have a look at its key points. First of all, to find its turning point, we're going to complete the square. And then to find the intercepts, we already established that we can't just factorize it. So to find the intercepts, so this is for the turning point, we can make that equal to 0. I will end up with, take the square root, plus minus 5, root 5, sorry. And then that'll be 3 plus minus root 5. Of course, we only need one of them because we're only doing one side. Now, for the inverse function, we need to swap the x and y values. We'll do it from this point here, which is in the completed the square form. It's a lot easier. And we just need to get y by itself. And you can kind of do it in one step if you know how to rearrange. So we'll take the 5 over, we'll take the square root, because it's a negative, the negative arm of it, it's going to be the negative square root, and then we will add 3. And that becomes my function there. Now I can go ahead and find the turning point and intercepts for that, but if you remember, all the coordinates are just going to be flipped from the original. So all I need to do is really find the original key points. So our turning point, which is 3 and -5. And our intercepts, most likely it'll be the -1 that we will need. So that'll be 3 minus root 5. And then we can just flip it for the new function. All right, so putting this on a pair of axes, y. So we will have our key points. We've got a y-intercept of 4. We will have an intercept of 3 minus root 5, and we will have a turning point of 3 and -5. So just trying to keep to scale as much as we possibly can. See if we can draw a curve here. I think it's going to end up being a little bit funny when I try to get it to snap into place. That should do. And so we can put in all of our key points. That's 0, 4, 3 minus root 5, 0, and 3, -5. And for my inverse function, it's going to be the same, but all of the values are flipped. So I'm just going to put in the line y equals x first of all, so I can see that mirror reflection. So it should be something like that. And I'll draw the new function in, try to keeping to scale as much as we can. So that would probably be our 4, 0, flipping it around. And then we want -5 and 3. So that should be something around there. And remember, we want to aim for it to intersect along the line y equals x. Now again, I'll try to draw it as best as I can. Doesn't quite snap into place as I want it to, but close enough. All right, so all the x and y values are just flipped. 0, and then this one will be 0, 3 minus root 5. Okay, so that is simply how to draw an original function and its inverse. Now, as we were just talking about, the theory that's most recent is about finding the points of intersection. So this wants us to find the points of intersection between the two. You can imagine that if I try to equate these two functions, it's going to be quite ugly. So trying to equate square and square root, but instead I can just equate one of them to equals x, because that also happens to intersect with the line y equals x. So I'm just going to equate the original function, because I don't really want to deal with square roots if I can avoid it. And I'm going to make that equal to x, and now we're going to go ahead and solve for x. So it's just going to require a little bit of algebra in this case. Now from here, you can complete the square, you can do the quadratic formula, whatever you find easiest. I might go ahead and just complete the square. So we'll take half of the middle number, and then we will square it and add 4. I'm just going to straight away turn it into the fraction so I can add it easily together. So that'll be minus 35 on 4. And now I just need to rearrange to get x by itself. So first I'll do that. Then I will take the square root of it, plus minus, and then I'll add the 7 on 2. So we can see that the point of intersection, because it's the negative half of the parabola, is going to be the negative section. So if we continued on, you can see that this would be the more positive value. So the lower value is minus. So the value that we're after is 7 on 2 minus, and if I just simplify that, that'll be 35 on 2. Now, the great thing is that because this is the line y equals x, whatever the x value is, that's just going to be the same as the y value. So the point of intersection will be 7 on 2 minus root 35 on 2, and it's the same value, root 35 on 2. Okay, so that's the intersection of the graphs. All right, there's one last little section to this exercise and then we're done. So composite functions with inverse functions. So we've spoken about composite functions last lesson. Now we're talking about it in terms of inverse functions. So there's something really interesting about when we put it together. So remember an inverse and an original function, all that's happened is we're flipping the x and y values. And a composite function is where I have an input, I'm going to get an output. Now, if I put that exact same output back in, then I'm going to get the same input that I started off with. So the idea is that if you were to do the composite function of an original within its inverse or inverse within its original, you actually just get whatever you started off with, the original input. So if you just started off with x, you get x. If you started off with 2, you get 2. If you started off with a squared plus 5, you get a squared plus 5. So here's an example of how that works. If we've got g of x is 3x plus 1, this is the inverse here. You can see that if I were to substitute the inverse, so to make it a composite function into the original, first of all, the 3's will cancel out. I end up with x minus 1 plus 1, which means I end up with x. So whatever the original input is here, x, is what I'll get out. And that works both ways. So for example 12, we're just going to practice this idea here. It says if f is from 1 to infinity and so on, find f inverse. So we'll just find the inverse to this. So it'll be x. We'll just get y by itself. So then the inverse function, and you can write it out in its full notation, especially because they've given it to us in full function notation. I'm just going to do the same thing. So that's part A, just finding the inverse. Part B then says to sketch f inverse of f of x over its maximal domain. So that's really interesting, right? So f inverse of f of x. Now you can go ahead and substitute in and do whatever. And in fact, I'm going to do it just so that you can see, but I hope that you can recognize that it's going to just be the same as whatever the input is. So that's going to equal x. But let's go ahead and give that a go. So f inverse is x squared plus 1. And f of x is root x minus 1. So I'm going to go ahead and substitute that into there. And look what happens. So when I take the square root, that cancels out. I end up with x. Now here's the thing though. It's not just as simple as sketching the graph y equals x. As you can see, it clearly says over its maximal domain because we have to remember the properties of composite functions. Now, remember the domain of the composite function is equal to the domain of the inside function. And the inside function in this case is the square root, and the domain of this function is from positive 1 to infinity. So that's the square root that has been moved over by 1. So we are in fact looking at the graph y equals x, but it has a restricted domain to be that of the inside function, which is from 1 to infinity. We'll draw up a set of axes. And so we'll draw y equals x, but it is specifically from 1 to infinity only. So you need to understand the rules of everything. You need to understand the rules of the inverses. You need to understand the rules of composites, everything to be able to draw this graph here. Okay, finally for part C, this is just a bit of a test to see if you understand how this works, the inverse and the composite together. Remember, whatever the input is going to be whatever the output, the final output is. So I started with x plus 2 equals 3, on 3, sorry. If I take the inverse of the original, I'll end up with x plus 2 on 3. Now you can go ahead and practice this. I'm more than happy for you to try that after the video, just to see whether that comes out as true or not. But because you're taking the inverse and the original composite, whatever your input is what your final output will be. Okay, so that's the end of this exercise. See you next time.